Welcome to Networks Professionals.
Welcome everyone to this explainer. Today we're unpacking a concept that honestly has one of the absolute best, quirkiest names in all of network engineering. We're talking about router on a stick, or ROAS for short. But, don't let the funny name fool you, as we're going to see this is a highly efficient setup that elegantly solves a really common, very physical problem. If you've ever wondered how to cleanly route traffic between multiple VLANs without creating just an absolute tangled nightmare of cables, well, you're exactly in the right place.
Here's our roadmap for today's explainer. We'll start with the core concept, then look at how the magic actually works, weigh the pros and cons, and finally, jump into some Cisco configuration in action.
Let's dive right into Section 1, the concept, and how we go about solving all that cable chaos. Okay, so picture the old way of doing things. Routing 5 VLANs meant literally using 5 physical cables to connect 5 switch ports to 5 physical router ports. It's messy, it eats up those expensive hardware ports, and frankly, it's a nightmare to manage. The router on a stick method replaces all that chaos with just elegant simplicity. Instead of that mess, we use a single, dedicated trunk link connecting the switch to the router. And rather than burning multiple physical interfaces, we're utilizing multiple virtual interfaces. Now, the absolutely crucial point here is the sub-interface. What we're doing is taking one physical router port, let's say gigabit Ethernet 0/0, and we're logically dividing it through software into multiple virtual interfaces, like gigabit Ethernet 0/0.10 or 0/0.20. It's kind of brilliant, right? Because each one of these virtual sub-interfaces acts completely independently as the default gateway for its specific VLAN. So one single physical port is suddenly doing the heavy lifting of many. Moving on to Section 2, let's see how this magic actually builds through a 3-step process. It really comes down to this highly orchestrated 3-step dance. Step 1 happens right at the switch. The switch port connecting to our router is configured as a trunk. So when traffic from a VLAN hits that switch and needs to be routed, the switch slaps a specific tag onto the packet using 802.1q encapsulation. That tag? That's the secret sauce. Then step 2. The router receives this tagged packet, reads that 802.1q tag and says, okay, this belongs to VLAN 10. It instantly routes it over to the exact corresponding sub-interface. And finally, step 3, once processed, the router sends the newly routed packet right back down that exact same single trunk line to its destination. It goes up the stick, gets routed, and comes right back down the stick. All right, Section 3, the pros and cons, because we all know we have to weigh the trade-offs. Look, network design is always a balancing act, right? Now, what's really interesting here on the pro side is that this setup is incredibly cost-effective. You're only burning a single router port and a single switch port. So for smaller networks that maybe don't have the budget for those expensive Layer 3 routing switches, this gives you massive flexibility. But we have to look at the cons. Because you're forcing all your Inter-VLAN traffic through one single physical link, you are inherently creating a potential bandwidth bottleneck. If traffic suddenly spikes, that single cable can get super congested. Plus, it creates a single point of failure. If that one router port goes down, well, all Inter-VLAN communication literally stops completely. Let's ground this in reality with Section 4, Cisco configuration in action. It all starts with the physical hardware. Before we can even think about slicing a port into virtual pathways, the physical port itself has got to be turned on. So, in the Cisco CLI, we enter our physical interface, gigabit Ethernet 0/0, and we simply issue the no shutdown command. We're really just waking the port up here. And notice, we don't assign an IP address yet. The physical port itself remains totally unaddressed. Once that physical port is awake, we exit out and create our very first sub-interface. Here, we type interface gigabit Ethernet 0/0.10. That .10 is what actually creates the virtual interface. Then, we apply the absolute most critical command, encapsulation.1q10. This is what tells the router to listen for those specific 802.1q tags coming from the switch specifically for VLAN 10. Finally, we assigned it an IP address, 192.168.10.1, which now serves as the default gateway for everything living on VLAN 10. And this brilliantly illustrates how scalable this setup really is. Because to add our next network segment, we literally just repeat the exact same process. We create interface gigabit Ethernet 0/0.20, we tell it to use .1q encapsulation specifically for VLAN 20, and we give it its own unique default gateway IP address of 192.168.20.1. Just like that, utilizing only 3 lines of code per network segment, a single physical interface is now successfully routing multiple isolated networks. It's that clean.
So what does this all mean for you? You've got your subinterfaces configured, your tags are set, and your router on a stick is logically complete. But what happens if you test it and your pings from VLAN 10 to VLAN 20 just time out and fail? Did you maybe miss a trunk configuration on the switch side? Or, looking at the bigger picture, if that bandwidth bottleneck we discussed earlier starts to really choke your network, at what point do you abandon this method entirely and upgrade to a layer 3 switch? That's where your true journey as a network engineer really begins, and it's exactly what you should be investigating next. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.
Thanks for watching.